Yeah, thank you for the introduction. My name is Seiler. I'm a senior data scientist at Control Expert in Germany. Some words about my background. I'm working for 20 years in software development, and 5 years ago I decided to specialize on data science, which was actually a pretty good decision, I would say. In 2015 I joined Control Expert as a data scientist, and my focus there is predictive analytics. One of the projects that I've been working on is the topic of my talk today. In that project I applied machine learning to automate a particular part of an existing business process. These are going to be the themes of my presentation. I briefly talk about Control Expert's domain and vision and explain the business context of my predictive model application. Then I will outline typical steps of any data mining project and share some best practices of major parts of the process. Software engineering is very useful to streamline your work when you work in machine learning. And since I've developed mainly in R, I share some best practices and tips and tricks about that as well. At the end of the presentation, I outline some of the factors that led to the success of my project. So let's get started about Control Expert's domain and vision. Control Expert drives digitalization and automation in automotive area. Our customers are insurance companies, leasing and fleet companies, car dealers, garages, and OEMs. We rethink service and claim handling and aim for simplification and automation of the entire process. Today, Control Experts operates in 14 countries and processes around 25,000 claims per day. In Germany, almost all of our customers from insurance companies are our customers. So let's have a look at Control Expert's core process to understand where machine learning has been applied. Here the core process of the claim handling is visualized. So in step 1, we receive the claims in different formats, being paper, scanned documents, or already digitally. In step 2, we extract the data and bring it to a standard format. Step 3 already analyzes the claim automatically, checks against reference data, and applies some rules. And step 4, we have 250 car experts who check the claim manually from a technical perspective. At the end, we create a report and ship that back to our customers. So the machine learning question here was, how can this business process be automated? And in particular, can the manual check process be automated? So this is the solution we came up with. We built a classifier that is capable of separating the claims in two classes. OK means the claim is probably correct and does not require a check by an expert anymore, whereas not OK means the claim is probably not OK, not correct, and should be checked by an expert. This means that OK claims can be shadow processed without human intervention. This shadow processing has obviously a couple of benefits. It reduces the time for checking claims, the OK claims, and we have less work for our car experts, and the processing of the OK claims is faster. The machine learning challenge was, how can we build a classifier that is accurate enough to allow this shadow processing without sacrificing the overall quality of the claim check? So let's see how we achieved that. A data mining process is quite complex. Luckily, there are some common steps that have been defined already 2 decades ago. And one concept is crisp DM. It's very useful, it has been defined. It's cross-industry standard process for data mining. It's still popular and especially very useful if you start with machine learning. So this is crisp DM. There are several steps that are in principle followed in sequence. There are some steps back and forth necessary in order to accomplish one task, and then if you have finished the first version, you can run the overall process again. In the center of the process is the data that you have or that you need. First, in my opinion, often underrated step is gaining a business understanding. For my project, I just briefly talked about the business context. For example, in order to get a domain understanding, I could get in touch with our car experts. In order to get business expectations, I got in touch with our senior management. The next steps are in more detail outlined in my presentation. Just briefly, in the data understanding step, you get in touch with the people who create or provided the data. In data preparation, you check for missing data, outliers, you transform your data and make it ready for modeling. In modeling, you experiment with different models, since you typically do not know upfront which model is the best. Before applying the model to the real world, it comes to evaluating it. And finally, you deploy your model into a production environment. This is, of course, very simplified, but I'll talk about the details next. The first 2 steps I will talk about is data preparation and modeling. At this stage, you need to consider what kind of machine learning problem you want to solve. And you need to select for an algorithm. I will come to algorithm selection later. In my case, the problem space was defined by, I had structured data. I would like to build a classifier for 2 classes, which is a binary classification. And I have historical data from the claims, so I can use supervised learning for my training. So data preparation and modeling is an iterative process, and it has several steps. Select, clean, engineer, and model. You run through all these steps until you have a first satisfying model, and then when it comes to improving the model, you run again through all the steps. Step 3, engineer, is a bit of an exceptional step. It might not be relevant in one of your first model runs. It might not be relevant at all. I will talk about that in a minute. So let's have a look in detail. Select features means you would like to find data items that have predictive power. Of course, you can just take all the data that is available, use some statistical methods to find correlations between the data and your target class, or you can just feed everything into a model algorithm to let the model algorithm find out. But you can also do something else. Remember, in my case, we have an existing business process, and we would like to take a decision instead of a car expert. So maybe the car experts were the right people to ask for good features, not from a technical perspective, but from a business level. I got answers like, if you have a new car, a very new car, then it's more likely to be not okay, the claim is not okay, because of the complicated technical structure. With that information, I could ensure that, for example, age of the car model are part of my data. This is, of course, no guarantee that these are good features and have predictive power, but that you can still find out. If you have a lot of features, not in my case, but in principle, you could have a lot of features, you may run into a problem which is known as curse of dimensionality. Simply spoken, you have too many features so that your algorithm cannot find a solution in an acceptable time. There are different approaches, dimensionality reduction, for example, They're very well known. But you can also remove weak features, and that is what I've tried. Several model algorithms provide means, importance measures, for example, to identify weak features. There's some support in tooling available. I will come back to that later. Your learning target Y is maybe not just a column in your data, but might be constructed out of other data. And your training data is part of the business process, so the data may change over as part of the business process. So we need to select the right revision for your training data that is available at prediction time. Typically, data in real world is incomplete and has implausible values. Of course, it depends on where the data is coming from and where it has been created. In order to judge on how to overcome these flaws, you need to understand the data well enough. You can get in touch with the people who created or provide the data in order to understand where the gaps are coming from. There are ways to interpolate missing data. Alternatively, you need to remove the examples from your training. Business people may help you to understand plausible value ranges in case it is not obvious. In order to compare different model algorithms or to speed up your training, it's often necessary to transform your data. For example, categorical features can be converted into binary features, so-called dummy features. Numerical values can be normalized, so they are between 0 and 1. This typically improves your training quite drastically. Different model algorithms are more or less sensitive to missing data or wrong data and so on. For example, decision trees are less sensitive. But since you typically would like to compare different models, it's always a good idea to transform and clean the data up front. As mentioned earlier, engineering features is an exceptional step in your machine learning pipeline. Before the deep learning era, it was common to engineer features. As an intuition, with your domain knowledge, you construct features out of individual data items that are more useful for your learning target as individual data items. Formally, you find a higher level representation of your data. That is what deep learning is about. It learns higher level representations out of lower level ones. I've not used deep learning in my project, but engineered feature in a traditional way. Again, our car experts were the right people to ask about potential good features. Once you have constructed the features, you can check the usefulness with a model run. Unfortunately, feature engineering is very time-consuming because you need to run through all the steps for each feature that you construct. For my current project, I'm trying out deep learning, but it also requires a lot of data in order to learn the features. As soon as you have your data prepared and you can start with modeling. But there are plenty of algorithms out there. Which one you should try? This is not at all a comprehensive or complete list of possible choices. Still, I would like to give you an intuition what kind of factors are relevant for your model selection. Starting with the type of learning. In my case, I had a supervised learning problem. The learning target, whether it's being a classification or regression, is typically not a problem for your model algorithm. Most of the algorithms support both out of the box. I've listed a couple of algorithms here, which I would try. There are, of course, a lot of other algorithms, but these have a track record of excellent performance for supervised learning. Of course, there are other type of learnings which I will not further outline here. The next question is, what type of data do you have? In my case, I had structured data in form of database tables and XML files. The type of data gives you a hint whether deep learning or shallow learning needs to be applied. With shallow, I mean traditional machine learning algorithms, so not deep, not learning features. For images or text, no one would doubt that deep learning is the way to go. But for structured data, it depends on the amount of data that you have. Two factors are relevant here: the number of training examples and the number of features. If you have a lot of training examples and a lot of features, then you can try out deep learning, definitely. If you have low number of training examples, and in particular low number of features, then it becomes hard to learn features. Then shallow learning or traditional machine learning is still a good way to go. There's a theorem in machine learning known as no free lunch. Actually, this means every machine learning problem is different and one needs to train with a specific data at hand. Also, you do not know upfront which model algorithm performs best on your training data. That you can only find out with experiments. A very useful tool for your experiments is plotting a learning curve. That is, you change a parameter, just a parameter in a serial of runs, and observe how the error is changing. Every model algorithm has its own so-called hyperparameters, which control how the algorithm is working. You can easily tune the hyperparameters with several runs and plotting a learning curve. Once you have a first model, the question is how to improve. A very good source of information is analyzing the errors or the misclassification. For example, do the misclassification have something in common, a pattern? Maybe you need more examples of that kind. Or you need a feature that helps to overcome the misclassification. Luckily, there's some tool support available. I will talk about that in a minute. Once you have a first promising model, the question is how to evaluate it. This is actually not a one-time task, but it's part of the iterative development. The question is, how will the model perform in a real production environment? This is for those of you who are not yet familiar with machine learning. So, from your training data, you keep a holdout that you don't use for your training. That is a test data set. With this test data set, you go into your model algorithm and predict the values for your test data set. Then you can compare the predicted values and the true values and calculate a certain metric. For different machine learning problems, there are different metrics available. I've made very good experiments for the binary classification with the so-called ROC curve. So let's have a look. This is a ROC curve. So ROC means receiver operations characteristics. There are several possibilities how to plot a ROC curve. Very common is a true positive rate over the false positive rate. In addition, the so-called cutoff value is visualized here. I will talk about that in a minute. A ROC curve addresses several issues at the same time. First, you would like to know how accurate is your model. For evaluating accuracy, you can use the area under curve, AUC. The larger the AUC value, the better is your model. This metric has been used for decades in machine learning as an overall performance metric. However, some papers show that AUC has some flaws when comparing different model algorithms. So I will not use AUC for selecting a certain model algorithm, but it's still very useful if you would like to tune and fine-tune and improve the model algorithm that you have chosen. Here you see different AUC values plotted. The diagonal line at 0.5 is not at all a good classifier. It's comparing to rolling a dice. When the model is getting better, it bends towards the upper left corner. And in theory, the best model would be a rectangular with AOC 1.0 with false positive rate 0 and a true positive rate of 1. The second issue that you would need to tackle in the binary classification is deciding on the cutoff value. This means at which probability you decide for the positive or the negative class. This is a trade-off. At a given model accuracy, you can think of shifting the error from false positives to false negatives. In other words, you need to decide on which error is more costly. Let's recap for my project. In my project, positives were shadow processed claims. Negatives were claims that are routed to an expert. That means that false positives are wrongly shadow processed claims, whereas false negatives are claims that are wrongly routed to an expert. You can easily see that wrong shadow process claims are very costly, and the other ones that are wrongly routed to an expert do not do any harm for the overall quality. So we decided that a false positive rate from a business perspective of 1.5% is still acceptable for our shadow processing. You can read then from the ROC curve that the expected true positive rate of this model would be 10%. This means our classifier is able to shadow process 10% of the OK claims, which doesn't sound too much, but simply due to the high quality expectation, and the model is not good enough. We have evaluated our model and have an idea about the expected performance in the runtime. So now we need to decide on putting the model into production. As it turned out, the deployment has its own challenges. Looking back, I would recommend not to wait too long for going into a production environment, at least trying it out. Maybe at this point, the work can even be split. While one developer is still continuing on improving the model, the other developer is working on the deployment. So let's recap for my project. We have OK claims, we have not OK claims, and the OK claims are bypassing the manual check. And so let's see how this looks like from an IT perspective. This is the IT perspective. We have a workflow. So above the line, you have the part of the claim processing workflow, which is relevant for the prediction. You have the data extraction, you have the manual check. The idea was to hook in the classifier between those sub-processes, and the classifier is running on a separate analytics machine as a web service. It is called from the workflow via REST API. Then the result, being it OK, not OK, is returned to the workflow and is used here to bypass the manual check or not. That's how the workflow works. Before putting the shadow processing live, we decided to test the prediction at runtime. So we switched off the detour around the manual check and stored the data, the predicted values, in a database instead. Now we could run the workflow collecting predicted values and manual check values at the same time. And after a while, we could simply compare the results. Result was the predicted values were completely wrong. The reason was I used the wrong revision of the data. So with a small fix applied that could easily be deployed, after a while the results were OK, and we could go live with our shadow processing. This is now working for over a year now, helping us to improve our business process. While your model is running in production, there's new data coming in that you have not used for your training. So there are two aspects here. So new data can be used for your training to improve your model. Typically, if you have more data, the model is better. The other thing is the new data that is coming in may not match with the current model. So your model is gradually deteriorating and getting worse. So that need to be under control. You can easily do that by updating your training data with new data and running a new model run and check the performance. With a build script, you can easily automate the creation of your model. When your model is running in production for a while, you have a lot of claims that have been processed by your model prediction. The question was, should claims that have not been processed by an expert be part of the next training? And this sounds like a trivial question, but it isn't. The answer is yes, it needs to be part of the next training. Otherwise, the model would learn a bias towards the not okay class. So you simply take away the examples that are okay. A machine learning project can be compared to a software development project. And software engineering is a technique that can help you here to be more efficient. So let's have a look how this can be applied in machine learning as well. Source control is very useful in order to keep track of your changes and your different models. You can easily see which model version led to a certain model result. In order to keep downtime of your production system low and reduce the risk of a failing deployment, you can work with different environments. So ideally, you have three: a development environment, a test environment, and a production environment. Once you have different environments and you often deploy new models into the production, it makes sense to think about easing the deployment. So you can use some deployment tools, writing some scripts, for example, that may help you here. Since we are using a REST-based web API, we can tools like Postman for automatically testing the web service. It's very easy. There are a lot of machine learning tools out there, commercial ones and also open source. Under the open source tools, R and Python are certainly the ones that are very popular here in machine learning and data science. I used R, and on top RStudio as a development environment. As you may know, R has thousands of packages for almost all applications. Its strength is coming from being first-hand a statistical tool for data exploration, but it has also a lot of packages for machine learning. By the way, I think tomorrow there is even a workshop for machine learning in R, if you're interested. But I can also share some tricks here. We need to repeat the steps from data preparation up to modeling over and over again. In addition, we need to experiment with different models. This means that time becomes soon a limiting factor in your project, and you need to think of ways how to use your time efficiently. Also, R provides the power of parallel computing. With a couple of packages, there are a couple of packages available, and they are very easy to use. With just a few lines of code, you can set up a so-called parallel backend, which consists of either cores, CPUs, or even machines. Other packages can utilize this parallel backend for computing in parallel. I would like to mention two packages. The for each package runs loops in parallel, and specifically for machine learning, the CARET package is very useful. It lets you compare and tune your models in parallel. We will look at CARET in a minute. Ultimate goal is to have more model experiments at the same time. So let's have a look at the CARET package. It's definitely a must-have if you work with machine learning in R. It helps you in almost all the steps of your machine learning pipeline. I've listed just a couple of features that CARET has. But the most powerful feature is the model comparison, tuning, and optimization. Almost all machine learning models are hooked in a library and can be just used, and with just a definition you can compare different models. Every model, as I mentioned, has its own hyperparameters. The good thing is that CARET knows these hyperparameters and the plausible value ranges. So it can, when optimizing your model, CARET knows, okay, let's tune this hyperparameter from this way unto this way. Finally, CARET uses the parallel backend and tunes and compares your models in parallel all at the same time. As we saw in the deployment view, we developed our prediction as a web service. The good thing is that R provides a module which is called R Apache. So you can develop a web application and still continue to develop in R. Configuration is very easy with just a few lines of code in Apache configuration file. As part of the configuration, you can define that all the R sources, and in particular your model, is preloaded so that the execution time of your prediction is minimized. Standard with Apache is to handle several requests in parallel. So you can run several requests in parallel, several predictions in parallel. This is also supported with R Apache. The response can be provided, for example, in JSON, so that the integration to the higher level workflow is just a one-liner. Before I conclude my presentation, I would like to share some of the factors that contributed to the success of my project. They might not be relevant in your project, but may give you a hint what works well. I was very lucky to have all the machine learning process steps in my hand. I just provided a web service that my colleagues could integrate it into the higher level workflow. I know from experience that this, especially in larger machine learning projects, is an exceptional situation, and typically you work in a team. Maybe this is a no-brainer, but keeping the team small improves your efficiency, because especially in machine learning, the turnarounds are very short. So the smaller the team, the less people you need to consult and ask, the better it is. The second important factor was I was co-located with the depending parties. So from domain experts or IT experts up to senior management, I could meet the people in person. Again, from experience, I know this might be an exceptional situation, especially in big companies. However, nowadays you can utilize high-quality virtual meeting applications, preferably with video, so that you can keep the virtual team closely connected. Last but not least, it was very useful to have an agile development mindset. What does this mean? You work in a short time frame, which is called a time box, in order to complete a small feature. You deliver as soon as possible a minimal valuable product. Each so-called sprint runs through all the process steps that we have, from data preparation up to modeling. And finally, in agile development, you welcome change and failures, because this ultimately lets you improve. At the end of my presentation, I have tried to condense everything into one slide. So let's see whether this makes any sense. This looks like a brain. If you remember this crisp DM process slide, then you find that this looks like very similar. Just to wrap up, you start with understanding your business and your data before you wrangle your data and make it ready for modeling. Then you experiment with different models, or with the one you have chosen. You should not wait too long before going live, and test and run your prediction service in a live system. That's it. As a side track, you could follow engineering techniques to streamline your development. And finally, I've listed have fun. For me, machine learning is sometimes hard, but mostly fun. So, thanks for your attention.